It's both sound and video, so it'll be okay. I think it might be a little bit directional too. It might be mostly hearing that side. So. What's up, man? What's up? How's it going? It's going.
Hey, welcome back.
Hey, why are you not coming to Senate?
What do we have? We have something else ready.
Yeah, I know.
Another Christmas party, but. Something else in mind, we're doing, oh man. I was afraid of a good one, I wouldn't do that.
Yeah, you don't know?
Make it in there for dear life. You have run back afterwards?
What's that?
You gotta run back afterwards.
Oh, to campus?
Yeah. So if I got 5 minutes of your time,
Sure.
I only got 5.
Oh, okay.
That's all it is. I was trying to outline the hybrid, heavy hybrid
Yeah.
vehicle project. And trying to find the sweet spot, which complements stuff and gives me a
Okay. Fabio, maybe you can close the door. Okay. Oh, my gosh. Okay, so we are ready to start. Welcome to everyone. So today is Guido's Day, right, for his PhD. So we have here all the committee members, Fredrik, Monica, Greg Shaver, and John Lucas here. So I need to introduce Guido. As I said, is his day, a very nice day for him. Bittersweet day for the advisor, because when the PhD student finishes, it's always an accomplishment, but also it's a little sad that he's leaving, especially when students they work hard to get not only the PhD done, but also to serve the lab, because Guido, since his beginning in 2012, he started at the beginning of 2012, and since the beginning he started contributing to the work of all teams, not only for the system group, but also for the pump group. He got the chance to destroy a couple of pumps as well, right? And, but it was really nice. So he did his work on oscillation damping, and we'll give him the floor in a second to describe us what he has accomplished. But he contributed in several projects, and that is always very nice for an advisor. And so it's a good example also for the other students that are here, I'm sure. So, Guido, you can start with your presentation, and we are looking forward to listen what you have to tell.
Yeah, thank you for the introduction, and I also like to thank the committee members for being here and to serve in my committee, Professor John Lomkus, Guido Scherer, and Professor Ritelli. And I would like to thank everybody for being here and listening to my PhD defense. So the title of this presentation, which is the title of my thesis, is Active Oscillation Reduction in Hydraulic Flow Handling Machines with Energy Implications. So going through the outline of this presentation, I will start, of course, with the motivation, the state of the art, and I will state clearly the research goal. And then in the first part of this presentation, I will talk about the first part of my work, about the dynamic pressure feedback, in particular the cost function formulation and the experimental auto-tuning on the machine. I will open a small side discussion about the energy consumption considerations I performed on the experimental setup. And in the second part of the presentation, I will go through the novel frequency-based control for focusing especially on the payload oscillations reduction. And I will wrap this presentation with the conclusions and my main contributions. So the motivation of this research is, of course, vibrations. Oscillations they affect hydraulic machines, and the main sources of oscillations are the flexibility, the compressibility of the fluid, and they can also be present in machine implements. They can also be caused by disturbances or discontinuities in the input of the machine. And the natural oscillations, especially on these heavy machinery, are high amplitude and low frequency. And the consequences can be many. Among them, we can list the reduced productivity of the machine, safety issues, and also oscillations can pose health hazard for the operator, and also they can reduce the life of the machine. So looking at this picture, which is a general example of a truck loading crane, we can see how oscillations can take place in different places. So we can have structural oscillations, which are oscillations strictly related to the hydraulic system and mechanical parts of the machine. But we can also have oscillations, for example, in this particular case, on the cabin and on the payload oscillation. So what has been done so far about the structural oscillation? Of course, there is a fairly large amount of research done in the past. And we can recognize two main families of these solutions they use to reduce oscillations on this machine. We can see pure hydraulic solutions, which make use of the resistive effect of, for example, orifices, or capacitive effect of, for example, capacity, additional capacity or accumulators in the system. And we can also have electrohydraulic solutions that are more recent development, and they make use of controllers, which use in turns information from sensors of the machine in order to generate a proper signal to the machine. So going through the first category, and there is of course a third family, which is a mixture of these two methods. So going through the first family of these, of the pure hydraulic oscillations, if we look at this very basic and general hydraulic system where we have the power supply, the motion control system, and the hydraulic actuator. So the first solutions for oscillation damping were developed by controlling, for example, in a valve control system, controlling the meter in and meter out orifices. And as I said, there is a very large amount of literature present on these two topics because they were the most direct and natural way to realize oscillation damping. And then, of course, as I said, we have also solutions where we can see the addition of additional components, such as orifices on pilot stages of valves, or the use of accumulators. And great examples of these solutions are, for example, in load sensing systems, orifices in the pilot lines of the compensators, which are the main component of a load sensing system. A great example of inline solutions are counterbalance valves, and where the particular use of particular settings of these valves can actually also attenuate the oscillations of the machine. And other great examples for the capacity effect are, for example, the use of accumulators, which is very common on, for example, wheel loaders, where they use accumulators to reduce the oscillation of the boom, especially while driving. For the electrohydraulic solutions, we can see here another very general hydraulic circuit where now we have a sensor which sends pressure, position, acceleration, depending on the solution. And this information is fed to an electronic controller together with the operator command. And the output of the controller, which can be, as you will see in a minute, open or closed loop, is sent to the electrohydraulic components in order to generate a proper signal to the machine to address oscillations. And as I said, there are two main categories, open and closed loop solutions. Especially for mobile applications, open loop solutions are probably the most used today because they are also straightforward. Because usually these half-moving machines, they are commanded in open loop, where basically the operator closes the loop. And very simple and very surprisingly widely used solutions are the use of ramps or low-pass filters to smoothen the operator command in order to make the machine response smoother. There are, of course, of most recent development solutions for closed loop controllers, where we have the pressure feedback, which is of particular interest for my research because it's what I use in my research. But we also have examples of position feedback and adaptive control, and also in pump control systems, especially in this lab, we see a lot of research. And so to summarize these solutions, unfortunately, pure hydraulic solutions, they can show additional energy losses in the system or machine slowdowns, and they are generally not flexible because once you realize the solution, you have no way to change the parameters of the system so that solution will be optimal for a particular operating condition. Electrohydraulic solutions are more flexible for sure, but they can pose reliability problems on the machine since we rely on a controller, and they are also very often tailored on a specific application or a specific machine. So again, they are not very flexible. And so all of them, they share a common ground, which is that there is probably the totally lack of generality of these solutions. For cabin or payload oscillations, where we have oscillations taking place in different positions, in different locations on the machine, there is really something missing in literature, because generally the authors for all these techniques for oscillation damping, they usually assume that a smooth operation of the machine is reflected in a smooth operation of the payload, which is true in many cases. For example, in excavators or wheel loaders, where the load is kind of part of the machine, so if the arm is stable, the load will be stable. But this is not the case of load handling machines, where the payload is actually mounted or attached to the machine in a flexible way. So it can generate different modes of oscillations. And in other fields, of course, this is a major problem, and we can list fields such as gantry cranes or offshore applications. And so in these fields, one of the most important control was one of the first controller developed was the Posicas control, introduced by Schmidt in 1957, where basically the approach of this control is to split the command of the operator in two steps, and every step is separated by from the other step of half the period of the oscillation. And this is something that you can also intuitively see if you imagine a simple pendulum. If you split the motion of your arm, you can cancel the residual oscillations. And the natural development of this technique was the input shaping. And the first paper introducing the input shaping was by Singer in 1990. And Singles, especially with this paper from 1994, he really developed the input shaping technique. And this is very, very similar to the Posicas control, where now they split the input in different steps, in multiple steps or impulses, in order to cancel residual oscillations in the machine. There are also examples, very recent, of input shaping applied on hydraulic machines, and here are the two examples I was able to find. This paper from Moon from 2012 and this paper from Magnus from 2015, so very, very recent. They actually applied the input shaping on the motion of the boom of the machine, and also in this second case on the swing of a crane, and but without load. And also the input shaping is very effective when you command a machine using a step command, which is not the case of general hydraulic applications where we want to control the machine in a proportional way. And another big field in payload oscillation damping is the heave compensation. I'm citing this paper because it's very close, somehow similar to what I did to address payload oscillations. But the heave compensation is somehow different from what you would imagine as payload oscillation, because they only care in this case about the vertical compensation of the payload. So when they have to place something on the seabed, they just want to compensate the motion, the vertical motion of the boat. And this is another example of some very interesting solutions. So in this case, we have a very recent paper from Lee, 2012, 2015. And in this case, he uses a vision feedback, so he uses a camera to track the payload oscillation and try to counteract this oscillation. But unfortunately, this solution first I don't think it's applied, but also it's difficult to apply in our case where machines they work in very unsafe environments, so the damage of this camera will be very, very likely. So the goal of my research was to generate a general solution to address these oscillations and try to find potential energy saving associated with this general solution. And so the main question my research wants to answer is, can we make an automatic procedure to find the optimal parameters for any operating condition for the controller, and can be this technique realized by modifying as less as possible the machine, and can be generally applied to different systems. Another question I try to answer is, can this methodology show energy saving potentials, and also how to address other sources of oscillations, for example the payload, and if this solution can be applied to these cases. So here is the controller architecture I used in the first part of my PhD, and so it's called dynamic pressure feedback, which is actually something not really new, because and I'm citing this paper from Cruz because it's something related to my research, and what I'm going to tell you in the next few slides is also something taken from the previous student which worked on this topic, which was David Cristofori. He graduated a couple of years ago. So the technique, here you can see a general linear actuator moved by a directional valve, and then we have the operator command. So again, this is an open loop solution. So the operator command goes directly to the valves, and we have a superimposition of another